Okay, so thank you everyone for attending this session, and thank you for to the organizers for arranging this every year now since let's say the COVID-10 really great conference. So my name is Thomas Feggeler. I'm a postdoc at UC Berkeley and the Advanced Light Source at Lawrence Berkeley National Lab, and I'd like to tell you something about how to see localized gigahertz dynamics in magnetic, let's say, nanostructures and microstructures using time-resolved scanning transmission X-ray microscopy. So why it's interesting to study such things, or especially magnetic nanostructures are nowadays, well, let's say, known for their capabilities to be used in cancer treatment, gene therapy, DNA probes, spintronics, magnonics. And we have standard techniques like magnetometry, thermomagnetic resonance, micromagnetic simulations, Lorentz TEM, GM holography, to name a few. And also to see here some examples, for example, angular dependent FMR of a Fe3O4 nanoparticle chain with micromagnetic simulations in addition, TEM holography on Fe3O4 nanoparticles. And these techniques are all really great. What they usually all lack, let's say, except for energy resolved TM, is element specificity. And here comes the excess magnetic circular dichroism, and of course, for antiferromagnetic materials, the linear dichroism into this. How can one do dynamic studies with such thing? By basically a technique called X-ray detected ferromagnetic resonance. And when we add that to a scanning transmission X-ray microscope, we end up at time-resolved scanning transmission X-ray microscopy. So how does such thing work? So really briefly, the real detection scheme is a little bit too much for 12 minutes. So what we basically built is, or have built, is a huge lock-in amplifier. So we are creating a phase-locked loop between the synchrotron frequency and our excitation frequency, and by that realize a stroboscopic recording with some sub-picosecond time sampling of our magnetization dynamics. The main element of the setup is the so-called Stickson or scanning transition X-ray microscope, where we focus with a Fresnel zone plate our X-rays onto a sample, eliminate lower intensity diffraction orders with a so-called order sorting aperture. And for the dynamics, we position our sample in a so-called microresonator, so a lithographically created resonant loop, usually made out of gold. And this is positioned between the poles of an electromagnet or also a permanent magnet construction. And below the sample or behind the sample, we are detecting the transmitted X-ray radiation with an avalanche photodiode, and then implement our excitation scheme. How does such a measurement work? So basically, we are recording two sets of data. Here on an example of a cobalt stripe deposit on a paraboloid disk. This is a measurement at the cobalt L3 edge, and we are recording a data set with the microwave excitation turned on and one with the microwave excitation turned off, and have here a fixed phase difference of 60 degrees between the time points. And when we create the difference of these two data sets, we can extract the FMR or microwave-induced X-ray transmission, here shown for the uniform resonance of the cobalt stripe. One can clearly see the expected sinusoidal behavior of this resonant response of the cobalt stripe, and so the localized XMCD contrast here from our measurement. Furthermore, we introduced the color coding scheme. So when we are looking at this stripe here again, especially at this dot here, so we have again a sinusoidal behavior of our resonant response. What we are doing now is taking the resulting final set of images after the difference of the microwave off data, and fitting a sinusoidal to each row of images for each pixel row, and then color code the phase and the color hue, the fit accuracy of the color saturation, and the amplitude as a brightness. And by that, we can, let's say, demonstrate different phase responses from the magnetization in a, let's say, single image as the sum of the different images we recorded. This means for this stripe here, we have a different phase of the magnetization between the stripe edges, the stripe center, which is of course explainable by the stray field influence, which we have here. So to look further into some data, so we are back at our cobalt stripe on the permaloid disk. So now we also mention here the dimensions here. We have a 2 micrometer length of the stripe and 0.5 micrometer width, and thickness is 30 nanometers on a permaloid disk with a diameter of 2.5 micrometers, also with a 30 nanometer thickness. Conventional ferromagnetic resonance spectra, here now focusing on the main resonance lines, shows us basically 4, let's say, larger resonances or main resonances, which we name here as 1, 2, 3, and 4. So the fourth one at the time of the experiment was out of our static magnetic field range. So we will concentrate here on these 3. And the excitation was done at here at 9.27 gigahertz. And we want to know now with time resolved Dixon what these resonances, where these resonances originate from. So here we have example images of our measurements measured at the nickel F3 edge and the cobalt F3 edge, and the different resonance fields we see here from the conventional spectrum. And what we see here is for the first resonance, so the permaloid disk is basically showing a uniform XMCD contrast with a higher M intensity area here at the position of the cobalt stripe, while the cobalt stripe itself at the cobalt edge just shows on the oblique excitation, which is the explanation that we have the main resonance of the permaloid here, and this is driving over exchange coupling the cobalt stripe into precession, but the cobalt stripe itself is not excited at this field. For the intermediate resonance, we see again the permaloid disk pretty uniform in contrast. We have a higher contrast area again at the stripe, and we see a very darker contrast for the cobalt stripe. This is we call it coupled resonance, that permaloid and cobalt resonate basically as a coupled entity. And finally, the main resonance from the cobalt, which we have seen before. Here we have again the similar situation that the cobalt now weakly drives the permaloid magnetic moment into a weak precession. Weak precession means at this relatively high field, most of the permaloid moments are already pretty much aligned to the external field, therefore just this weak response. Looking at this permaloid stripe ensemble, what we have here, so with this vertical and horizontal stripe with the given dimensions here, we will look at the resonance we see here from the micromagnetic simulation at 112 millitesla, and at this frequency, which is 9.426 gigahertz. We see inhomogeneous excitation of our of the vertical permaloid stripe here, showing a spin wave mode. The animation consists basically of these 6 images we have here, and here we have this amplitude phase evaluation image, basically showing that we have a phase difference between the stripe edges and the stripe center, with higher amplitude areas here at the stripe edges. What is remarkable that we basically have in this confined geometry, something like a directed oscillation from the edges to the center, which is, since we expect a let's say a standing spin wave mode in this confined geometry, pretty, let's say, remarkable, like I said. And we see the same similar situation in the micromagnetic simulation for that. So basically the explanation here is that we have the phase gradient of the magnetization driving this directed oscillation, which results again from stray field influences and the excitation of resonant edge modes. So going to nanostructures, iron oxide nanoparticles with magnetotactic bacteria. So depending on the orientation and arrangement of such particles, one can shape basically the magnetic dispersion, as we can see here in a conventional ferromagnetic resonance spectrum. And we also wanted to look at time resolved Dixon to such a chain. So we have here this 19 particle chains in 2 segments with a size of 40 to 50 nanometers per particle. And we did a micromagnetic simulation using this model here, showing basically what is probably expected, of course, that we have here in this dipolar strength intensity color map, strong dipolar coupling between the particles, a weaker one between particle segments, and again, strong particle coupling in this main segment of the chain. Also, the stray field map shows us that we don't not only have interparticle coupling, but also coupling between the particle segments. And now I would like to draw your attention to this example here, showing basically the simulated resonant response of the MZ component at a field of 166 millitesla at 6.748 gigahertz, showing a strong resonant response in this main curved part of this chain. And sorry. And we did time resolved Dixon on that. Here you saw sometimes also called Dixon FMR. And you see already here the color-coded amplitude phase representation. So we have a uniform phase in our whole sample of about 280 degrees. And we see a high amplitude area in this curved part of the chain. You will wonder where are the particles. Since our spatial resolution with normal Dixon at the iron L3 edge at that time was limited to 50 nanometers, we couldn't resolve the single particles. But let's say basically the shape of the chain. Here's the 4-particle segment, this displaced particle at the curved section. With additional micromagnetic simulation and the same analysis methods, we could show that we really see this relative phase difference to the time point t equal to 0 of 280 degrees and could confirm the high amplitude area in this curved part of the chain. Going briefly to a more complex arrangement, which you can see here. Basically, we see here now the animation of multiple particles at the resonance at the same time, showing these resonance centers, R2, R3, and R1. And when one goes to different fields and different frequencies, unfortunately, we have lost some parts of the chain during the measurements. We can see different phasic excitations between these upper particles and the lower ones. And with that, I come to the conclusion. Time resolved Dixon itself offers element-specific analysis of magnetic materials, also with dynamics down to 17 picoseconds at the moment, with resolution below 50 nanometers. We showed the dynamic excitations in permolar cobalt B-line microstructures, permolar strap ensembles, and every 0.4 nanoparticle change. And the outlook for the future is that we want to bring this technique to so-called time resolved X-ray photography, which uses computational reconstruction of Dixon data recorded with the CCD camera, and by that bring down the spatial resolution to below 7 nanometers with the cooperation partners you see here. And with that, I'd like to thank you for your attention.
Thank you very much, Thomas. This is great.
Hi, can I have
yes.
Oh.
Thank you.
Oh, thanks so much, Thomas, for the great talk and a nice introduction to this beamline. A quick question on so why the SEM picture can show the magnetic resonance behavior in your measurement?
The SEM, or you mean the Dixon?
Oh, yeah, ST.
Yeah.
Scanning
so basically, Dixon is spatially resolved XMCD. And XMCD basically is a technique you are using X-rays to probe core electron states of your material. Basically, you're probing the empty states at the 3D above the Fermi energy of your material. So if you can excite basically core electrons to that, and by using circular polarized X-rays, this is sensitive to the spin orientation of your electrons. And by that, you're getting magnetic information. This you can use as spectroscopic information and as microscopic information. In short,
it's kind of visualization of the XMCD signal.
Right. So basically, it's a spatial resolved visualization of XMCD and XMLD.
Mm-hmm. Yeah, so actually I have the experience in using the Beam 402, which also do XMCD and XFMR. So I just want to, you have a quick comment to what's the difference or any advantage of the STXM compared to that beamline?
So the spectroscopy usually is more sensitive on the gathering spectroscopic information. So the XFMR beamline will give you basically the spatial resolved spectrum of ferromagnetic resonant excitation, while STXM gives you the spatially resolved information where you can, for example, locate in which material or let's say in which component, which material of your sample resonant excitation, let's say, is localized. So you can basically get local information where you have your excitation. And for example, you can use that if you want to characterize magnonic or spintronic building blocks for spin transistors, directional couplers, and so on, that you basically can follow experimentally your excitation and visualize where it originates, basically.
Yeah.
And of course, you get also chemical information from by that. So the usual things that STXM can basically.
I think we should move to the next speaker. If we want to continue a discussion, we have